mass balance, and kinetics together. Please prepare the table with the formulas to calculate the volume for the kinetics topic. That's something that you might not need to use it, but if you need it, you need to have it. I'm not going to provide it, so please keep it handy. I would recommend a hard copy. I think that is easier to handle, and then you can use if needed. So please keep that one prepared. I will send you another email if there is anything else needed that you need to prepare. Not really notes this time. Don't worry about it. That's for risk assessment. So later, not now. And I believe that that's all for the announcements today.
I have a question.
Yes.
We're talking about reading notes. So the reading notes for this Wednesday's quiz, is it all we have to include on there is stuff about mass balance and kinetics, right?
There is no reading notes for this quiz. Only risk assessment and beyond.
Oh, so then what kind of notes are we turning in for this Wednesday on the quiz then?
For this Wednesday, you don't have any notes to turn or submit, just the risk assessment and beyond. For this one is as the other quizzes. I just mentioned that you need to have prepared that last page of the kinetics handout that has formulas for the time calculation.
So we do have to so for this Wednesday, we have to turn something in of our quiz. It's it includes definitions and theories about kinetics and mass balance. Then on the other side, I could have formulas.
Not for this quiz.
Oh.
She's talking about the handouts that we use in class.
There's a handout that we use in the kinetics handout. The last page has a lot of formulas that please make sure that you have them prepared.
So we're not turning in anything before the quiz this Wednesday?
The mass, I just removed the agenda, but we have the practice problems, right, are due on Wednesday.
So we're turning the practice problems in before the quiz on Wednesday. Got that. But okay, as well as asking if we had to turn in any kind of notes or something right as we start the quiz or something like that.
No, there is no reading notes for mass balance and kinetics quiz.
Oh, okay.
All right.
That's what I was confused about.
Let's move on. And if you have more questions, come and see me, David, during office hours.
Okay.
All right. Okay. So let's move on. I'm going to share my iPad to remember what we were talking about last week. I do believe that we ended up in here. And we did the exercise of going into the breakout rooms and finding the risk of contracting coronavirus as expressed or reported in different media or online sources available, right? So, and you notice that it's different depending on the city and depending on the activity that you do. So risk is going to be associated to a particular activity, but also could be associated to a location. So just to recall quickly, but very importantly, to make sure that everybody comes on topic with me, we talk about 4 different important parts of risk assessment. The number 1 is hazard identification, and then the dose response assessment. Number 3 is assessment, and number 4 is the risk characterization. So we're going to be talking about those 4 different stages. If we finish all of them today, otherwise the number 4 probably is going to be until Wednesday. So we also talk about the EPA regulation of 1 times 10 to the minus 6 as a potential acceptable risk for people. And when I send you out to bring out the risk for contracting coronavirus, you were telling me values about number of people in a given number of population. So the 1 times 10 to the 6, I just want to make sure that this is clear. So I want to expand a little bit more on that. 1 times 10 to the minus 6 is equal to 1 over a million. Okay, so some of you found fractions. So that would be 1 person in million people. And that is a risk that is acceptable according to EPA. And when probably you already thought about it, the risk of contracting coronavirus is way larger than that. That's why we need to be very careful. We need to wear masks or avoid some places. Some places are closer to this high risk of contracting coronavirus. So we're going to be looking at different ways of expressing the risk. But remember, it's 1 in 1,000. I'm sorry, in 1 million people, and that's what is acceptable. So we're going to be handling this and converting back and forth from a fraction into or a small number, 1 times 10 to the minus 6, into a ratio. Okay, so let me see. I wanted to show this slide. Where is? Maybe it's not here. Okay, so it doesn't matter. Let me go to the workbook here, and then if I really need to, I can go to the PowerPoint on my computer. But I want to make sure that we start in here. So we're going to start with number 1, the hazard identification. And many of you probably by now already read the chapter. The reading notes are not due, but hopefully you have started and read some of the parts. Just to make sure, I'm going to go a little bit faster. Help me or ask me questions if there is any question that you have. When we talk about hazard identification, we need to talk about toxicity. How toxic is something? And the toxicity is going to be measured in 2 different ways. We have what we call acute toxicity or chronic toxicity. Any of you have any idea what is the difference between them?
Acute is like short-term exposure. Yeah, and the chronic is long-term.
So acute, it will be short-term. But in terms of concentration, do you think that how small or large the concentration will be?
Smaller for acute?
Smaller for acute? Anybody else? Everybody agrees with that?
Yes. Is this compared to chronic? You're comparing acute to chronic?
Yes, both of them are opposite. They're opposite. So if acute is short, chronic is long. I'm going to give an example that many of you may or may not be familiar with. We call chronic pain. I don't know if you know someone with chronic pain. What does that mean? Or a chronic illness. What does that mean?
That it can't be gotten rid of. It's kind of, there to stay.
It's forever. It's long term until they're alive. So long-term chronic, right? And when we talk about environmental engineering, acute and chronic is associated with a concentration of chemical. If you remember, we're going to be going into dose later down the road, number 2. So toxic, and what is toxic is going to be depending on how much we're exposed to in a given time. So in acute, I don't know why always associate acute with sharp, like something very like pointy or extreme. I don't know if that will help you, but short term is going to be associated with high concentration. Now, what is a high concentration? That is enough to call a lethal response. When we talk about acute toxicity, most of the time, if not all the time, is going to be related to lethal. Yes, it's going to be related to mortality. And we'll talk more about this. So acute exposure, that means short-term exposure at a high concentration, where we are going to be talking about a lethal dose. And then chronic toxicity is going to be long-term exposure associated with a small or smaller concentration. Okay, and usually is effect with time, affecting health. We're talking about human health with time when exposed to smaller concentrations. Example, I do believe that everybody has been driving on the freeway during peak time when a regular half an hour drive takes you 3 hours. Do you think that during that time you are ingesting any gas from the other cars that are surrounding you?
Yes.
Yeah.
A lot or just a little bit?
Probably a lot.
In a small time or long period of time?
I would say a small period of time.
Small period of time if it is one drive, right?
It just depends.
It just depends. Well, it is recommended no more than 8 hours on a peak hour like traffic, because then you're going to be getting what we will call acute effects due to the contamination or the exposure of a gas that is coming from a car, exhausted from a car. So if you're driving and it's going to be less than 8 hours, let's say 2 hours and 45 minutes, or probably even less because the exits and entrances, then that's no longer on the freeway. Hopefully it's not going to be more than 3 hours. And whatever the concentration is going to be exhausted by in the car, then you're going to be exposed to chronic term, long term, if you're doing the drive 5 days a week because you're heading to campus or you're heading to work. For 30 years, or because you're working, or if you're studying, it's only for 4 years or 5 years. So that will be long term. That will be long term and a smaller exposure because hopefully you have the windows up and the AC and the filter, the AC going on and the filter circulating the air inside rather than bringing the air from outside. So if you're not doing that, make sure that you do something like that when you're driving. So fortunately, one drive like that is not going to be causing, unless it's excessive amount of CO2, for example, it's going to cause any poisoning or any effect. Maybe you're going to have a headache because it was 3 hours long and you didn't have the windows up and you were smelling the gas, inhaling the gas. So maybe you're going to have a headache, maybe you're dizzy. That would be an effect of the exposure for one time, which is going to be causing already a response. So we're going to be talking about that and classifying in two very general, two different ways. Acute, which means short-term exposure to a high concentration that is going to be most of the time resulting in a lethal dose or the end of the life, which is not what we want to have happen. And then the other one will be chronic or long-term exposure to a smaller concentration, and that could cause an effect in your health, but it's not going to be right away. So how long is enough, or how long is not too much or too much to be exposed? So we're going to be looking right now. It might be a little bit not specific. We're going to be doing some problems, and this is going to become a little bit more specific. Exposure for one day only, or we're talking about going and living in Denver, exposed to the UV light in Denver for 3 months, or other different activities. Also, when we talk about the hazards, we need to talk about two different definitions that are coming a lot when we talk about being exposed to different chemicals. One of them is mutanogenesis. And the second one is going to be the carcinogenesis. So mutanogenesis is when the genetic information and the genetic information is the DNA or the RNA molecules that we have in our body, and they are coded. They are coded the way they are, and that's why we have, like I do, black hair or the color of the eye. So it's coded and they cannot be changed. But something exposure to some chemicals could create or generate a change on this genetic information. So mutanogenesis is a genetic information change or modification. But this is going to be in a stable manner. So there is some change in the environment that might be triggering that order of the proteins or amino acids that you have in DNA or RNA, but it's going to be happening with time. The radioactive exposure to gamma radiation is one of the types of exposure that will be more certainly causing this type of mutanogenesis. Otherwise, it's going to be slower compared to the radioactive exposure. And let's talk about carcinogenesis.
Professor?
Yes.
What do you mean by a stable manner in mutanogenesis?
Okay, so a stable manner, let me go into another example that will be more stable. A stable will be like evolution. Evolution is a way of mutation of the cells that then are going to be resulting on changes in how the genes are expressed in our bodies. I don't know if you've read in literature, but some say that we're going to be missing the pinky finger because it's not very well. If we don't use it at all, it's not really useful for the functions that we do with our hands. So if that were to be true, eventually somehow our DNA will be changing in such a way that 1,000, 10,000, I don't know, 100,000 years from now, maybe babies will be born with only 4 fingers. So that will be more stable, it's slower, and will be resulting on many different things that are in the environment, not necessarily exposure to the contaminants. Now, exposure to contaminants like the radioactivity could also trigger mutanogenesis, and that could cause some change that tends to be stable to some change in cells. And if a female that was exposed to radioactivity, the cells underwent some change, and the embryo might be inheriting those cells with the new DNA that is modified, and maybe the baby is going to have, I don't know, some characteristics or feature that is different from other humans just because of the exposure to the radioactivity of the mother. Does that make sense?
Yeah, thank you.
Yes, and the book has like 3 or 4 pages on mutanogenesis and carcinogenesis if you want to go on and read a little bit more examples. And carcinogenesis, so it's very important to remember because everybody thinks, but aren't they the same? Well, yes. Cancer cells are mutants, but not all the mutants are or the cells that are mutated are cancer cells. So you can say that carcinogenesis is under mutanogenesis. So the carcinogenesis is when normal cells are transformed to cancer cells. And the only thing that I want to say about the cancer cells, because there is many kind of cancers, is that those cells start to grow exponentially. It's not at the rate of a regular cell. It's exponentially. They accumulate, and some of them are benign, and some of them are malignant. So rapid growth of cells, it's abnormal. Obviously, that's why it's called. It's a mutation of the cells that are in the human beings. And it has been proven that some of the chemicals that we use, or they are produced by humans, and some of the chemicals that are naturally existing in the environment, will cause cancer to humans. So that's why we're going to be studying these carcinogens when we go into the formulas. So remember, we are talking about hazard identification. So how do we determine what's toxic, or how do we determine what's hazardous? How to determine? What do you think? Any idea? What do you think that scientists do?
Maybe like test levels of radiation or test levels of harmful chemicals.
Okay, so perfect. So we're gonna be doing testing of chemicals, right? And so you said levels of radiation. What are you thinking? Something, an accident happened, or maybe just naturally happening and they're going and checking it, or what kind of situation are you thinking of?
Yeah, I mean, any situation where there might be higher levels of radiation than, in average, just in general, like any place where there'd be more radiation.
Okay, so why would there be more radiation in a place? For example, I don't know if you know about this event, Chernobyl in Russia. There was a nuclear reactor explosion, and the town was destroyed. There's still right now residues of the radioactivity, and a lot of people was hurt, dead because of the acute exposure, and also some of them that were not at the right center of where the reactor leaked. They were just reached out by the gamma radiation. So it could be human, let's say, related disasters. And then the scientists and the engineers know that the level of radiation should be higher than normal, right? They need to go and check what is that level, and they're going to be determining the level of the hazard. And now going into, so what is normal? Are you telling me that is a normal radiation in nature? Yes. Nature levels. So there's some places where radiation naturally occurs, and people have done a lot of research and testing, and they can, the scientists can determine where there is more radiation or radioactivity occurring naturally, and what are the normal levels in that place compared to LA, compared to Denver, or somewhere in the Pacific Ocean. For example, in Midwest, they have a lot of radon, and radon is a radioactive gas that is naturally happening underground. So depending on the type of structure that you're living in, and the for example, there's a field, there's a lot of fields in there. If there is a lot of wells or perforation done that are abandoned and they're open, they might be letting some of the radon come out of the surface, and the radiation is going to be larger compared to a place or a field that there is not that underground orifices that are connecting to the surface. And so that's one of the examples. So you could have natural levels measured, and then how much is too much. Investigators or scientists also can determine what would be a way that many people consider is unethical, but still helps for humans, right? A way to determine how much is too much.
Animal testing?
Animal testing. Thank you so much, Kelsey. So we do a lot of animal testing. So we're testing chemicals, right? And first we talk about in the environment. And there is a lot of animal testing happening. It's not preferred. There is ethically, a lot of people is not okay with it. But unfortunately, the policymakers said it is a need to make sure that we can protect the human health. So that would be a different type of topic on ethics. And it could be a complete class just going in right there. So let me go back to human-related disasters. usually disasters are not very common. Disasters are once in a while, one in a lifetime occasions. So when humans happen to be present in that type of situations, they actually come human studies, and that could involve tragedies like the Chernobyl event, like Katrina, and also they can be epidemiologist studies. Which kind of situation are we living with the pandemic right now? Is it a tragedy?
Epidemiology.
It's an epidemiology type of study. It's amazing. I have taught this class so many times and never imagined that I will be teaching this in the middle of a pandemic. It's crazy. We're gonna make history with this. So let's start looking around. And that's why everybody's collecting data about many different things, the coronavirus and the different activities and the risks. Just be very careful. As you will see on the plans that we're gonna be doing, they're reporting the number of tests, and sometimes they don't specify if the people is the population that they're testing is tested only once a week or once a month or maybe twice a week. So the number of testing is not really related to the number of people tested. So all of those different details are going to become very important when we're talking about risk. So you need to know more than just the number. You need to know more about where was this taken, what are the characteristics of the population, etc., etc., etc. All right. So now we know where we got the data. We get the data from human testing, or human studies. We don't do human testing. It could be tragedies, epidemiology, or from animal testing. And then when we do animal testing, there has to be some scaling factors, because usually the concentration that is given to the animals is very small compared to that one given to the humans. Okay. Questions so far? Okay, so I'm gonna go to page 4.8 on the textbook. Let me see, okay, it's right here, where we can see the weight of evidence category. This is a table developed by EPA, and is the first step to guide us into how dangerous is this, if there is sufficient evidence or not. So let's look into the different categories. They call it A, B, C, D, and E. So notice that we have animal evidence, and then we're going to have human evidence. Most of the human evidence, you know where is it going to be coming from, so it's going to be limited. If sometimes it might not be available or is insufficient if there is not enough people that got sick and there were not enough statistics on it. So if we have a group A is going to be a carcinogen. It's a human carcinogen. And if you notice in here, we have enough human evidence in that case. Even if we don't have animal evidence, probably there is enough cases of humans that have shown cancer due to exposure of this type of contaminant. So in the hospitals, they might be getting some data, maybe limited data, if there suddenly people is showing up and based on their questionnaires, they realize that everybody is drinking water from underground and it has been exported for this many time of years from the same town. And this kind of takes me to a movie, Eric Brackovich. I don't know if you have watched it. I believe that's Eric Brackovich, where it's in here in California. It's not related to it's related to arsenic, actually. That also causes human diseases. So exposure of a chemical long-term chronic could cause some effects. In this case, we're talking about cancer. And then we're gonna go at group B, and it's a probable, group B is a probable carcinogen. And group B is gonna be divided into different B1 and B2. B1, when we have animal evidence that is well, the human evidence, I'm sorry, is going to be limited. The level of the animal evidence is going to vary, but once it is human evidence in there, then it's going to be in a category that is a probable human carcinogen. In the case of B2, there is inadequate human data, so it's not as bad as B1, even though we have some animal evidence, or maybe there is not animal evidence. So if it falls between D and E, is going to be a not too bad situation. B1 or A, it's carcinogen or probable carcinogen, and there is some data there, so we need to be very, very careful. So when you're reading a report related to environmental engineering, and they give you some information, and you can see here the weight of evidence categories, A, B, C, or etc., then you know what you're looking for. You want to check if it is A or B1, and if it is, then you need to be very careful with whatever the chemical is that you are working with. Okay. So let's go back in here, and I'm going to change the page because it's starting to fade. So we talk about hazard identification and how do we look at the hazards. Now we need to talk about the dose response. Number 2, dose response. So I'm gonna give you here some drawings, some plots, very important. By the way, you need to learn how to plot these 2 different plots. Just by looking at the definition, should be very evident what's in there, and we're gonna develop a little bit of practice, so don't worry about it. So we have 2 types of dose response curves. The first one is going to be associated with the acute toxicity. Acute toxicity. They're very similar because they have on the x-axis, they have dose, and the dose is going to be expressed in the milligrams of the pollutant divided by the kilograms of the people or the person that is going to be ingesting per day. So for those, that is, or the units that we're going to be using. In the y-axis, if you remember, acute toxicity is related to short-term high concentration or high enough that is going to be causing a fatality. In this case, we're going to have mortality in the y-axis. And it could be percent, it could be out of like 100% or 1, or it could be number of people, depends on the data that is given to you. How this plot is going to be looking like, well, let me put it like this. Let me use the green. If someone is taking a dose and at the very beginning there is no effect, and we're not using any number, it's fine, but there's going to be a point that is going to start producing an effect. And assuming that this goes, let's just say it's to 1, all right? This flow is going to be, it cannot be more than 1, right? 100% of the animals that we are testing on are dead. So it's going to lead us to something that is very important, half dose. The center here of the curve is going to be representing 0.5 or 50% of the population tested. Is dead, right? So this is what we are going to call, let me actually use a different color, the lethal dose, or LD50. Every time that we talk about LD50, if a report talks about LD50, that means that is the dose at which 50% of the population of a study, it could be rats, it could be, you name it, any animal that is being studied, die due to the exposure at that dose. All right, so that's what we're, it's very important. Remember, acute toxicity is going to be associated to the lethal dose. Unfortunately, it's always targeting that because researchers and the policymakers, they want to know how much is too much, just to make sure that we keep our levels way, way far away from those doses. And if someone is exposed to that type of doses, we know that is very, very dangerous. All right, so how does a chronic toxicity curve looks like? It's gonna be very similar. We're gonna plot on the x-axis or dose, the milligrams per kilogram per day, and remember on the top the milligrams of the contaminant that is being ingested. In the bottom, kilograms is the weight of the person that is ingesting and the time that is ingested. So the time of exposure is important too. Now, since this is chronic, a little bit at the time, in the y-axis, instead of mortality, is going to be risk. What is the risk? The shape of the plot might be similar or might be not. So I put an S-curve in the acute toxicity just to show you one of the many type of curves that could be produced. I'll show you more. Don't expect that it's always going to be like an S. The chronic toxicity, I'm going to go ahead and draw it as an S2. So it's chronic toxicity. The very beginning, maybe there is no effect. The risk is very minimum or none. And then as soon as we see a response, the risk is increasing, and we're going to have our bell curve being developed again. In here, we don't really have the 50% population. We're just going to be looking into how the risk is going to increase as we increase the exposure to the dose in long term, right? And hopefully it won't be jumping from being chronic to acute. And the information that we get from the different groups is going to be slightly different, but fundamentally different. If you think about it, acute one, our acute toxicity dose response curve is going to give us the lethal dose. In the chronic toxicity response curve, we're going to get how the risk is increasing as the dose is going to be increasing. Does that make sense? What is the difference? Yes, give me thumbs up on your tiles or the participant list. I have it open, and then you can tell me if that makes sense or not. Okay.
Not sure it makes sense.
Okay. So there is another thing. If you notice the flat portion of in here, the flat portion of the plot is what we call the reference dose. So I'm just throwing out there some of the terms that you're going to be seeing on your textbook, and we're going to be using on the calculations. It's called a reference dose. Is when there is no effect, visual effect or response just yet from the dose that we are ingesting, or the person has, or the animal has ingested. And one important thing before I forget, for the chronic toxicity, the exposure is average to 70 years of life. So what this means is that whoever developed this based on today's life expectancy, they say, well, 70 years is what we're gonna be developing this for. If medicine improves more in the future years, and instead of 70 years of life expectancy, we move to 55, then this will be changing. Still, so far, we are using this as a 70 years life expectancy. So we're gonna be looking in there 70 years very frequently. Now you know where it's coming from. If you have a question or where is this coming from, ask me. I'll remind you that it's the life expectancy, but this is where the 70 years are coming from. It could change anytime soon. It really depends on when the policymakers decide to set up these numbers. I think it's very conservative. I doubt that might be going down. All right. The other thing that I want to point out on the plot, and I'm going to put it with the blue, I'm going to circulate here, is this, where the flat line starts going up. So I'm just going to extend the arrow in here so you know that I'm talking about that. It's called the non-observed adverse effect. Non-observed adverse effect. So before that point, there is non-observed adverse effect, but after that, they could be. And this is also known as NOAEL, NOEL. Okay, the NOEL point, then where there is non-observed adverse effect in your curve. All right. So now we're ready to start putting down some equations. Actually, for the questions, let me show you some more of the plots that we have in here. Is everybody ready to move to the, can I move to the plots? Are you done getting the info on the board? Yes? All right, I see some thumbs up. Perfect. So I'm gonna go to the PowerPoint. And actually, let me show you this. Okay. Are these acute or chronic dose response curves?
Acute,
Acute. Why?
because it says the lethal dose on there, and because on the y-axis it's percent mortality.
Okay, so you look at the two things. You got me, Maria. You know what was I gonna ask? Because it says acute toxicity, but if I ask you why, then you need to, you can read, but you also need to explain, and she explained it really well. We have the mortality in the y-axis. Okay, so this is acute. There is so we have two chemicals, chemical A and chemical B. Which one is more toxic?
It looks like chemical A.
Chemical A?
Mm-hmm. Because it's taken, or it's in reference to 1,000 people rather than 10,000. So it means like toxicity is more common with chemical.
Oh, 10,000 people?
I'm sorry, the dose is referenced to 1,000 compared to 10,000. So the smaller amount from chemical A is actually more toxic than chemical B.
Alrighty, so we're talking about mortality, right? The numbers in this plot represent something died, mice or some animal that they were being tested on. So the lowest dose resulted in 50% killing, right? And whatever is the dose in here, or chemical A resulted in a smaller dose. LD50 was reached with a smaller dose. Does that make sense? So when we compare the LD50s, 50% of the population killed and when exposed, and you know that the dose is smaller, that tells you that it is a worse or more toxic chemical. It's pretty straightforward, isn't it? Okay, so let's go to this other side. Which one is more toxic? Chemical A or chemical C?
It's chemical A.
Chemical A, why?
I'm not sure how to explain it though.
We don't see LD50 here, it's covered. I cover it. Someone is saying chemical C, why?
Area under the curve?
Area under the curve? No. It's not area under the curve. It's very similar to this one. Look, we have percent mortality on the Y, right? And we have those on the bottom. I just covered part of it.
C is more toxic because even at like 1 or 2 or whatever, there's still more percent mortality than A.
Okay, so it's being said that at any dose, right, shown in that is not covered, this line is higher, which represents higher number on the Y, which is higher mortality, compared to the numbers in here. Does that make sense? So let's pick a point. Let's pick a point. If we pick this point, which of them are going to have higher mortality?
C.
C. And if we increase the dose, which one has higher mortality?
C.
C. So the mortality for C increases and the mortality for A increases as we increase the dose, but C is always more toxic because it has higher mortality. Does that make sense? Yes? And I don't think that
I'm not sure I get it. So C has the higher mortality?
For the part that is shown, C has higher mortality. Yes. Now, I'm going to change to the computer because when I exported the PowerPoint in here, it covered it and it doesn't let me remove it. And I want to show what's on the bottom. So just give me a moment. This is on your textbook, figure 4.4. If you want to get it out, get it out. Let me stop sharing. All right, and now let me come here. Okay. Oh, you're seeing the wrong one. Okay. Okay, this is confusing. Okay, I found it. So it's the same PowerPoint. I'm just going to show you. Okay, so we are now here on the same slide, but on cover. Let's go to B. We're still here in B. I covered some of the part, right? And we were just looking, and we were looking at this. We said that in the portion that is shown, C is more toxic. And it is more toxic because at any concentration that we pick is going to result in higher mortality. Remember, the number on the y-axis is mortality, number of animals or whatever the population is, mortality. Now, if I remove this and we look passing LD50, which one? Use LD50 as a way to compare which one is more toxic, chemical C or chemical A?
Chemical A.
Chemical A, why?
Because a smaller dose is required to reach the LD50.
Okay, and many of you are agreeing on the chat. Chemical A is more lethal or more toxic because a smaller dose reaches the 50% of the population dead. So I have a question for you. Does the concentration has an effect on the toxicity of the chemicals? You have two different chemicals and you're trying to compare them. Does the concentration, low concentration versus higher concentration has an effect?
Yeah.
Yes, and many of you on the chat are also saying yes. So yes, when you compare two chemicals and their toxicity, you need to be very careful if you just use LD50 alone, you're just going to have an answer, and it's going to be completely different comparing to the answer that you will get when you have way smaller concentrations. Okay? So for small concentrations, maybe a chemical is more lethal than the other one. And a higher concentrations, and what is a high concentration is going to be determined based on the study. So we will need to have more specific information. What were the concentrations that we were evaluating in this study? 1 milligram, 5 milligrams, or maybe 20 or 60 milligrams. And when they plotted, what does this mean? So we don't have those concentrations right now. I'm not giving you a number, but we are looking at the concentration is when you are comparing to chemicals or 3 or 4 more chemicals is going to be very important to determine which one is more toxic. Okay? So study these plots, be prepared to look at them and answer questions on the quiz or the test. Comparing chemical toxicity is something that is very applicable, very practical, and we need to have practice with it. Any question?
So, Professor, for B, then chemical A is less toxic in smaller doses?
Okay, so for plot B,
yes,
chemical A is less toxic at smaller doses because? Yes, it's correct, Maria, but because? How can you tell?
Oh, well, I was actually just, it was my question.
Yeah, but it is because of the mortality is less.
So overall, if you asked us which chemical is more toxic, looking at the overall picture, is it still chemical A more toxic because it reaches LD50 with a lower dose, or is it more toxic?
Well, I think that depends on what I need to know. I need to be more specific on the question, right? Like when I was asking you, hold on, where is this? There. When I was asking you which one is more toxic, I cover one side of the slide or one part of the plot, right?
Yes.
The one that I was very specific on whatever I've been showing you, which one is the most toxic. In here, in the next one, oh my goodness. All right, in the next one, I'm asking you to look at LD50, compare them. And I'm very, very specific. So if I'm asking you something, which one is more toxic, in a situation like this, I need to be more specific. If you look at part A, which one is more toxic is very evident. You don't need more information to provide a very good specific answer. I don't think that I'm going to be asking you for a very general. And if I ask for a very general question, I will say, maybe it's important to be specific. You can say, I'm comparing LD50s. Based on LD50s, A is more toxic than C because the mortality is higher. Or maybe C is more toxic than A if we are looking at the portion, the lower concentration portion, and because the higher the mortality is higher. Does that make sense? So I'm always going to be asking you why. That's for sure.
Okay. Thank you.
Yes, no problem. So this is very important to understand. Things are way more complicated on the risk assessment side. We're not going to be going that complicated. I'm just going to be covering basic things. So if you decide to go for a master's degree in public policy and human health, you're going to be covering a lot of risk. All the complicated stuff of the higher level math is going to be there. In this slide, the only thing that is showing you, we're not going to use it, but it's there just in case, if for any reason there was a senior project needing this. If you need to extrapolate from high concentration to low doses, the low dose is going to be very important, and you will see because we need the linear portion of the line to be able to do some calculations to calculate risk. So the extrapolations from high to low is going to be important. There's different models to do that. This is one of the statistical models. It's called multi-stage model. It's on the textbook. So if you ever need it, feel free to go back in there. It gives you the basics on how to start. And but what we need to concentrate is on showing you different types of curves. So I am showing you now the dose response curves of what kind of toxicity. We have acute and we have chronic.
Chronic?
Chronic.
Because it's a risk versus a dose?
There you go. Because we have risk on the y-axis. Perfect. So now here we have 3 different type of plots. Based on the givens, which will be the more toxic? The higher hazard. And why? And we're not talking about mortality here. Higher risk. Which one? Let's call it, let me put in here. This is A. This is B. And this is C. In the chat, someone says that A, what is more hazardous? There's few of you that said A. Can someone give me the reason why? Why do you say that is higher hazard, higher risk? Oh no, I gave you the answer. But I need to hear it.
It would be because at the point you get higher risk, like at the beginning.
So what you're trying to tell me, just to make sure that everybody is with me, that at a given point, let's pick this point of dose. C has no risk, B has this risk, and then A has the highest risk. Is that correct, Enrique?
Yes.
Okay, so perfect. So I always advise you to pick a common point to compare the risk or the mortality, right? Because otherwise it could be different, like you saw that it could shift. So if you notice, this line, the A, it starts right at the origin. So any amount, any tiny, doesn't matter how small it is, amount of that chemical is a high risk for the human health. In this case, it's a non-carcinogen, but still it's not a non-carcinogen, but it's a risk if it is consumed. And then, so this is a linear plot. A linear plot could also be shifted to later, like here. So there is nothing happening down, and then all of a sudden goes linear. Or it could be exponential, right here on the origin, like B, or move, have a shift a little bit to the right, like C, and having a threshold here. A threshold is like the non-observable non-observed adverse effect. And it's also called threshold because there is nothing happening before. There is no risk, and then the threshold is right there. All right, perfect. So we need to get familiar with these curves. The next one is the most important point that I want to make in here. No, actually, before that, what kind of plot do we have in here? Is chronic or acute toxicity?
Chronic.
Chronic. Why?
It's a risk overdose.
It's risk overdose, yes. Even though it says probability of cancer, remember, risk is a probability. So mortality is not a probability. Mortality is an actual fact, right? The number of the population that die due to the exposure. Probability of cancer will mean risk. Perfect. So in here, I mentioned before, we care about the linear portion of the plot. Why? Because there is something that is called potency factor that we're about to put down and show you. So we have these lines, and the slope in general is going to be changing. Look at the curve in here. The S curve is going to have slopes as you move. It's different. So we just care about low concentration and the linear portion to be able to determine what we call the potency factor, and the potency factor is going to be determined from the lifetime risk or the risk and the chronic daily intake. So we are about to put this equation on the whiteboard. Chronic daily intake and the risk are going to be helping us on determining the potency factor. So I'm going to be switching from the computer to the whiteboard to put this down. Before doing that, I'm just going to show you this last plot. We have a dose response curve. And in here we see the RFD, the reference dose, the NOEL, the actual threshold, and the what says that is a non-carcinogen. So we're going to be talking about non-carcinogens and carcinogens that are, both of them are hazards for human health. So let me escape from here. Let me stop sharing. I'm going to go to the iPad. Is there any question while I'm the iPad?
The only question I had, Professor, was on that last chart. What was the LOAEL?
Okay, hold on. Let me. This one? Can you see it?
Yes, that's the one.
Can you repeat the question? Sorry, I was like concentrating on changing.
Oh, no worries.
Lowest observed adverse effect levels.
Oh, okay. Thank you, Matt.
Okay, so what was it? Still.
I was asking about the LOAEL. I didn't know what the acronym was for.
Okay.
Matt answered my question. Thank you.
And
right.
N is no observed effect level.
None observed adverse effect level. Yes. All right. Thank you, Matt. Okie dokie. Yes, it's a little bit disturbing to move from one equipment to the other, so I'm trying to minimize that. Thank you for your patience and for the help. All righty. So we need to go and talk about the potency factor. Let me use a different page. So the number one factor, this is going to be for carcinogens that we are going to be talking about, is the potency factor. And this is going to be, in your textbook says that's the incremental lifetime cancer risk. Let's put it incremental lifetime. I want to write it down here, but it's always just going to be the risk on the top, just to make it easier and simpler. And then it's going to be divided by the chronic daily dose. I'm sorry, intake, not dose, daily intake. And if you notice, it was the slope of the line, right? What line? Risk versus is called CDI. So this is CDI, chronic daily intake. Please remember that chronic daily intake is going to have units of milligrams per kilogram per day. And how do we determine? All right, so we define the potency factor, the risk divided by CDI, and now we're going to be going into the definition of chronic daily intake and how it is calculated. CDI has a, let me put it this way. This is a definition. Be very careful, because then the students are always like, no, you told me that was a question. No, this is the definition, and there is too much more to the definition. The definition is too complicated, and I've been thinking about skipping the definition, but I don't think that I can skip it. It's very important, and I'm gonna be pointing this out later when we solve the problems. The definition is very simple. It's the average daily dose So the units are going to be milligrams of whatever the contaminant per day divided by the body weight. The body weight is usually going to be, and this is kilograms, is going to be either an adult or a child. And those are going to be the variables, unless you're actually knowing the specific weight of the individuals that you are investigating or the little animal, then maybe going to be the weight of the animal. But this is a definition, okay? Be very careful. You can technically apply this formula to do some calculations, but you need to be very, very careful because you might be missing some important information. So with caution. I would rather go and use the formula that I'm about to give you that are expanded to include other important parts. So before I give you those, let me tell you that the lifetime is what? How many years?
70.
Okay, it's average over 70 years. Thank you. That was in the choir. All right, 70 years. Now, we're going to be very specific and classifying this in CDI to be used to calculate when we have drinking water problems or to be used in when we have contaminants in gas phase. So for water or drinking water situations, and I put water because it could be surface water. It doesn't need to be drinking water. For drinking water, obviously you will be following some of the drinking water standards. And for surface water, you will be following the surface water quality related. So we're gonna put this one in here, and the CDI is going to be equals, it's gonna be a long equation, and I'm gonna give you the units in there just to make sure that you remember, is concentration in milligrams per liter. So remember, if the concentration is given to you in micrograms, you need to convert it to milligrams to use the equation. And then this is going to be times the intake rate, and the intake rate is going to be in liters per day. And then we're going to have exposure, and the exposure is going to be in number of days in a lifetime. So what does that mean? It means that maybe the exposure is only 90 days in summer, right? When I was drinking the water from Denver or something like that. And then all of this is going to be divided by the body weight, which is kilograms, as we already mentioned, and then times 70 years, assuming that is a lifetime. And if you notice on the top, we have days per life, and on the bottom, we have years per life. So we just need to make sure that we convert our days in years, and we can get rid of the time units, or some of the time units, the years and the lifetime. So this is going to result in the units of milligrams, kilogram per day for CDI. And again, this is for water. We are looking into the exposure of chemicals due to the ingestion of water. Okay? And this is one of the questions that you should use in place of the one that is above, the one that says caution. Because if you notice, the one that is below is more specific to the actual details of the exposure. The one on the top doesn't really give you more information on the exposure. Okay. Now, if you notice, let me put it in blue. This concentration times the intake results in the average daily dose. All right? That is the one here on the CDI. So the only thing that is missing, the equation on the top, the one that we label as caution, is the exposure. So if you think about the equation on the top, the definition if you add exposure time, you technically are developing the equation on the bottom. And this is where many students in the test make the big mistake. They just use the definition without incorporating the exposure that is explicit in the problem. And they think that is correct, but it's not correct because you haven't incorporated the exposure. All right, so let me give you the next equation and then we are gonna end the class. For exposure, due to inhalation or a contaminant in the gas phase, CDI is going to be very similar. It's going to be the concentration. Now, the concentration of contaminants in gas is expressed, hopefully you remember, milligrams per cubic meter. The intake, we're going to have the same terms. The difference is the units. It's going to be in cubic meters per day. And the exposure is going to be the same. It's going to be days in a lifetime divided by the body weight in kilograms times the 70 years of life times the 365 days in a year. Okay? This is the question for a contaminant in the gas phase on the air, and the equation for calculating CDI for when we're drinking the water. It could be drinking soda if you want to think about that too, or drinking something. Usually is water. Okay, so we couldn't finish. It's fine. We're going to start doing problems next class. There is 2 more formulas that I need to give you: the hazard quotient and the hazard index, and then we are going to be doing 3 different problems and hopefully finishing. If we have a lot of questions, don't worry, that's fine. All right, with that, I'm gonna let you go. 2 minutes in advance of the time is fine. If you have questions, I'm here, and take care.
I have a question.
Yes.
So, as before, I just wanted to make sure. So, like, just want to make it fun to make sure. So, like, for the quiz on Wednesday, we don't need to like turn anything in before the quiz except for the practice problems. Right?
Yes, that's on Blackboard. Mm-hmm.
Okay. And then the reading notes for various risk assessment or they're due before our quiz for risk assessment, I think, right?
Yes, for when we have the quiz for risk assessment, you will submit your reading notes within the quiz. So there's going to be a place inside the quiz for you to submit the notes, and you can use those notes for you doing.
And we got to come up with our reading notes from reading the book, basically, right? So
yes.
Okay.
Mm-hmm.
Okay. And I think we have another test next week. I think I saw that like on the syllabus. I think the next one was for the 28th. I don't know.
No, probably we're gonna delay it.
Or is it too late? Or is it like too early to take it?
Well, we need to finish risk. I think that
so probably won't be next. So won't be
genetics, mass balance, and no, it's not gonna be. And you're reading my mind. I was planning on talking about that on Wednesday. So it's coming. I'm talking.
Yeah. So that's what I was wondering if I should already like this coming weekend like start thinking about the next test is coming like the 28th. That's what it's in the syllabus. That's why I was asking right now. I need to like.
No, we're gonna move that. I do believe that I already changed the date on Blackboard, but I'm not.
Yeah, you changed it.
Yeah.
Oh, it got changed in the syllabus?